Okay, let's start. So currently we are studying how to obtain or compute the inverse matrix of a given matrix. But at first, we need to check whether that matrix is a square matrix, right? And then once you are given this kind of a square matrix, and the question is we have to find this inverse of it, and then you just simply put your original matrix on the left part, and then on the right half you place the identity matrix on the right, and then do just row reduction until you obtain this reduced echelon form on the left part. So you started from this A and the matrix I, and then what you did is that you don't care what I is, or you don't care about the right part. You first try to make this left part of a given matrix A into reduced echelon form, and then if that reduced echelon form is an identity matrix, and then this part, the resulting matrix that went through the exact same processes from the identity matrix, then the resulting matrix will be your inverse matrix of A. And so we saw the reason why at the last part of the class in the last Tuesday. So starting from this A and I, and then we keep applying some row reduction, which is still multiplied as a matrix multiplication. Come on, let's see. Okay, so suppose that matrix was E1 and E2 and so on. So in that case, that row reduction is applied on the A, and then also the right part of identity matrix. And then suppose you obtained it as this identity matrix from this matrix input matrix A, and then suppose this identity matrix, after going through the exact same transformation, that was converted into C. And then if we split them into two equations, then we obtain this and then this. And so from here we can see that this part, which is multiplied on the left of an A, that is your inverse matrix of A. And then if we follow this matrix C, then it is just nothing but a multiplication of the exact same matrix on the left with the identity matrix. So this matrix C will maintain, or it will be exactly the same as all the multiplications of your row reductions from E1 through E4. And then from the first equation, we know E4 through E1 is your inverse matrix, and then that will become your C, right? So that's why we obtain the inverse matrix of an A in the place of C. Okay, so that was what we studied last time. And then let's think about the other case. What if you don't obtain the identity matrix as a reduced echelon form? So in this particular example of a 3 by 3, and then you started from this matrix, and then suppose your reduced echelon form was something like this: 1 0 0 and 0 1 0 and 0 0. Unfortunately, we have 0. Okay, so in this case we will have some matrix on the right, starting from this identity matrix, right? But the problem is you couldn't obtain the identity matrix as a reduced echelon form. And then that's when you can conclude that, okay, this matrix is not invertible. So no inverse exists for this matrix A. Okay? So you just try to do the same thing of row reduction until you obtain this reduced echelon form. And if that reduced echelon form is the same as an identity matrix, and then that's when this matrix is invertible, and then automatically this part will become your inverse matrix. But if row reduced echelon form is not becoming the same as an identity matrix, and then you don't care about what this part is, but your conclusion is this matrix doesn't have an inverse. Okay? So this is the whole story of this theorem 7. And then I just give a proof about why having reduced echelon form as an identity matrix is the same as invertible matrix, or the fact that you have an inverse matrix. Okay, so again, back to this theorem. Let's read through these two separate pieces, the first one and the second one. The first one is that the matrix is invertible, and then the second one is from the perspective of row reduction. A is a row reduced or row equivalent to identity matrix. Okay, so those two things are the same thing. Okay, so let's prove that. Okay, so let's start from the left and then see if the second part or the right statement is true. Okay, so let's suppose A was an invertible. In that case, A inverse will exist, of course, right? From just the definition of an invertible matrix. And then if we think about some linear system for whatever given B, then from the previous theorem, we can freely multiply this A inverse, which definitely exists on the left. Then this part will become identity, which is quite obvious, and so the matrix, the solution vector X will become A inverse B, right? So this is a one unique vector, which means for any given B, you will always have at least one solution, and at the same time, you will only have this one single solution. Okay. Okay, so in that case, we can see that this guy doesn't have any free variable, right? Because of the fact that we will always find the unique solution, which has this form, right? So which means we have only one unique solution, and so we have no free variable, and so every column should have a pivot in A. So if for this square matrix, for example, 3 by 3 matrix, in that case, in order to have these pivots in every column, it should be just this identity matrix, right? So there is no other possibilities. So having pivots in every column, and then in the case of square matrix, that matrix should be exactly the identity matrix in the case of a reduced echelon form. Okay, so that proves the direction. I mean, if we assume that the first statement is true, and then the second statement becomes also true. And then let's reverse the direction. So let's start with the the second statement, where your matrix A is row reduced to identity matrix. Okay, so this is our initial assumption. That's our starting point, and then we should arrive at the first statement. Okay. Okay. So in this case, so what we learned in this chapter, one useful thing is, in this case, we can always represent it as this guy: E1, E2, E, for example, 10. After going through 10 steps of a row reduction. Okay, in that case, we found this part to be multiplied on the left side of an A, which result in the identity matrix. So this is a part of the definition of identity invariable matrix. So automatically this part will become your inverse matrix. Okay, so that way, since we found the inverse matrix, and so A is invariable matrix, or A is invariable. So between these two statements, we can go from one side or one to the other, right? So that way, those two statements are exactly equivalent. Okay, and then so when explaining the process of solving or obtaining the inverse matrix, so I once mentioned, so last time I mentioned about this. So we consider, so given 3 by 3 matrix, we consider 3 different linear systems. So A is all the same, but the B1 is replaced by this guy, B2 is becoming this, and so on. Okay, so let's just manipulate. Okay, so let's manipulate or combine or integrate all these 3 different linear systems into one single equation, which is this guy. So A is this big, and X and B1, which is a 1, 0, 0, right? So another A and another X, which is an unknown, and then the B2 is 0, 1, 0, right? And then B3 is 0, 0, 1, right? And in this case, so each of them is a linear system, and then we can actually combine them together nicely into this form. So since we know, so given, yeah, it's almost the same thing that I just explained the last time. So if we have 3 columns in A, and then we linearly combine it, to obtain this resulting vector. So in this part, this X, so this is an X1, and then the resulting matrix, the resulting vector should be B1, 1, 0, 0. So this is an X1, and this is X2, and then it will become 0, 1, 0, X3 will become 0, 0, 1. Okay, so you can see why we can how we can combine all these into this one single equation. Okay, it's I mean, I'm trying to emphasize what we learned last time about the new perspective. So the columns are our ingredient on the left, and then we linearly combine it using this one set of linear combination coefficient to generate the resulting vector, resulting column vector. And then the second one is generated by using this linear combination coefficient. Okay, so basically you can see this kind of computing the inverse matrix, and this process can be understood in this manner. So you try to linearly combine your columns of a matrix A. So given 3 columns, you try to linearly combine them in order to obtain one resulting vector of 1, 0, 0. But in the second case, we try to linearly combine them to generate 0, 1, 0, and then 0, 0, 1. Okay, so if you can generate all these quite simple unit standard vectors by using or by linearly combining the given matrix, columns of a given matrix, and then that's when your matrix is invariable, and then that linear combination coefficient will form your inverse matrix. Okay, so I think this is a quite interesting and insightful way of understanding the meaning of an inverse matrix. So I think that's it for this chapter. Any questions? Okay, then let's move to the next chapter of characterizations of invariable matrices. So it's a quite short chapter, but it contains a really big thing. Okay, really one big thing. So that contains only this theorem 8. But theorem 8 is really large, and even worse, it will grow in the later chapters. So in maybe 2 or 3 weeks, we will add a few more items to this list. So it's not the end. So we have all the other lists. Okay, yeah. So all the way until the item L from A. This theorem is saying that all these different items are the same thing. I mean, they are mathematically equivalent. Okay, and then basically this is about this invariable matrix. Okay, so the simple statement of saying A is an invariable matrix, and then all the other things, okay, from B to L, all these items or statements are equivalent to this guy, which means, I mean, just like what we learned here. Okay, so in this case, if someone says your matrix A is row equivalent to identity matrix, and then that's when, yeah, we can conclude that your matrix A is invariable, right? And the vice versa. And that's it, exactly the same. So among all the lists, someone says one of them is true. So for example, let's pick up this guy. The columns of A spans Rn, and then your matrix is invariable. Okay, or your matrix is invariable, and then the columns of A spans Rn. I mean, that statement is true. But here, there is only one constraint or one starting point, even before talking about all the lists, and that is the simple fact of this square matrix. So we only discuss the square matrix. So here, there are some familiar statements, such as when viewing your matrix A as a linear transformation, then if saying that your linear transformation is 1-to-1, okay, that means your matrix is invariable. Okay, but this is not always true. But when we start with only the square matrix, okay, when we consider only the square matrix, and then this guy is the same as the invariable matrix. Okay, so and also these lists contains all the various things that we learned in the previous chapter. So for example, we can see 1-to-1 here, and then onto here. And then this spans Rn, that was the same as this guy, for example. So this long list will contain the previous theorems that we learned as part of this theorem. Okay, so in this case, if the equation has at least one solution for any vector B, so that, yeah, we already learned this guy is the same as the columns of A spans the entire space Rn, right? Okay, so we already know G and H are the same thing, and then also this guy was, yeah, what other equivalent statements were there? So what other statements are equivalent to them in terms of the pivots? So it's just a review. Okay, so when talking about G and H, for example, in terms of a pivot, what was the requirement? So if you guys remember the theorem, and then there were like 4 different items, right? And then the other one was I mean, the other one that had the exact same situation was that we have to have a pivot in every row in A, right? And then that was also the same thing as your linear transformation is mapping entirely onto the target or codomain space, right? So in this case, we do not differentiate between the M and N because we only talk about the square matrix. So if we consider this 3 by 3 matrix, and then the domain and the codomain, they are all in three-dimensional space, right? And then G and H, and then when studied this onto kind of transformation, you guys also know that I is also equivalent to G and H. So G, H, I are just one set of logically equivalent statements, right? So G and H, H and I are all the same thing. Okay, so we didn't even talk about the invariability or the existence of an inverse of a matrix A, but we can at least group them out of so many different items, okay, based on what we already learned. Okay, and then here we can see this one-to-one. And then this one-to-one thing was the same as, I mean, in terms of a pivot, we should have pivots in every column in A, right? Which means there is no free variable. And then in that case, this was the same thing as this guy. So no trivial, no non-trivial solution. I mean, in the case of a homogeneous linear system, if that system has only the trivial solution, that case is the same as the situation where we have no free variable. Okay, no free variable is the same thing as this guy. And then also, what about this guy? Columns of an A forms a linearly independent set. Okay, so D and E was the same thing, right? So that was that was kind of definition of linearly independent set, right? And then D and E and F, all these three are also one set of logically equivalent statements, right? Okay, then A has n pivot positions. So this is so we basically have two groups, okay? And then let's look at this C. And then this guy is also the same thing. So let's think about 3 by 3 matrix, and then the fact that the pivots are, I mean, every row have a pivot. That means every column should have a pivot, right? And then in the case of a reduced echelon form, that matrix should be identity matrix, right? So all these three things are the same thing in case the matrix is a square. So this guy, B and C are the same thing. A is a row reduced, or A has the reduced echelon form of an identity matrix, and then it means it has a pivot in every columns or rows, right? And so B and C are the same thing, and then B and C are also the same thing as the previously discussed two groups. At least, I mean, every rows have a pivot and every column has to have a pivot, right? So suddenly we drastically reduce the seemingly quite long list into really a small number of groups, right? So at least starting from B, okay, starting from B, and we saw that B and C are the same thing, and also D and A, D, E, F is the same thing, and then G, H, I are also the same thing, right? So starting from B and I, we now can understand all of them are the same thing, okay? Okay, then let's further go back to the upper part. So A is an invariable matrix, okay? And then from the theorem that we just learned in the previous chapter here, so we discussed these two things, and then they are the same thing, or logically or mathematically equivalent. So that is actually just the equivalence between A and B, right? So identity matrix as a reduced echelon form, which that means your matrix is invariable, right? So that was exactly the theorem here, right? So we now extend it further and then handle this, the very first item, A. Okay, so starting from very first item of an A through I, they are all the same thing. Okay, so up to this point, I think you guys should be quite clear. And then let's just handle the remaining item of J, K, and L. So yeah, when considering J, K, and L, okay, so let's also handle let's take care of the easiest one among the remaining thing, which is the L. So so starting from A and I, they are all the same thing, so we can pick up whatever we want, right? And then start from there, and then arrive at the new item L. So among the A through I, let's pick up the first one. A is an invariable matrix. And then let's try to prove A transpose is also invariable matrix. And then this is we already proved it in the, I think, let's see, in this chapter, I think. Let's see. Maybe in the second chapter. Yeah, this guy. So if your matrix A is an invariable matrix, and then A transpose is also invariable, and then its inverse matrix is actually the inverse of original matrix, and then applying the transpose. Okay. So using this relationship, let's think about A is inverse is the same as A transpose is inverse. Okay, so in this case, it is quite easy thing. So if A is an inverse, and then you guys know A transpose is also invariable, right? Because the inverse of A transpose is represented as this equation or this expression, right? So from this, we can definitely say that the inverse of A transpose exists, and that inverse has this form. Okay, so since the inverse matrix is existing, we can say that A is inverse, and then A transpose is also invariable, not inverse. Okay, A is invariable, then A transpose is automatically invariable. And then if we start from this A transpose, and then we treat that as A, and then A is like A transpose of transpose. Okay, so we can easily reverse this direction, right? So those two things are also logically equivalent. Okay, and then in case someone might have some question, let me ask this in advance. So why? So when studying these lists, so currently we are looking through these lists, but why do we talk about the case, I mean the opposite case, when the matrix A is not invariable? So why are we not proving or not considering what if matrix A is not invariable? And then still, are these statements are true? I mean, they are logically equivalent, which means, so in other words, so this theorem 8 is only saying the situation when your matrix A is invariable. So what if your matrix is not invariable? And then can we not use any of them? But this is a, I mean, if it's a kind of fundamental question or issue about logically equivalent. So which means, suppose A is not invariable, then by the fact that they are logically true, we can also say that A is not row equivalent to identity matrix, and also we can also say that A doesn't have n pivots, right? So that way we can easily discuss the converse or the other contrary situation, okay, the opposite situation. And then how can we say that? I mean, why is that true? Why is that true? Why is that true? So if so if you study the logic or the proof based on this logic, so if you know A is B, then this is logical equivalent to not B is not A, right? That is the same thing, right? So suppose you prove this guy, and also when B is true and A is also true, okay? In that case, not A will lead to not B, right? So it means, so in this case, if A is true and then B is true, and then if B is true and A is also true, okay? But if we look at the counterpart on the right part, and then it is also saying that B is not true, and then automatically A is not true, and also if A is not true, then B is also not true, right? So that way, so if they are all equivalent, then if A is not invariable, then not B is true, or A is not true, right? Which means A is not row equivalent. We can definitely say that as well. So that way we don't, we don't need to consider this opposite situation where A is not invariable and things like that. Okay, so so for this, so we proved or understood this both direction being true, right? So we took care of this last item L, and then this guy is happily joining our list, and then the remaining thing is these two things. Okay, JK, then so let's look at the book. Okay, so among the long list, so these are the exact same list, and then these two items are the ones that we didn't handle yet. Okay, so let's see, J and D. So we have all these and all these as just one single logically equivalent set. And then what we want to do is to start from one item among here and then jump into J, and then we want to come back to one of the item in our list. Okay, so that's our strategy. So in that case, let's start with an A. So if A was an invariable matrix, then this guy, there exists some matrix C that satisfies this thing. Okay, so yeah, so if A was an invariable matrix, and then this was actually the definition of the inverse matrix. So if A inverse exists, then you can just simply plug that into the C. And then A inverse times A will become identity. Okay, so it will be, yeah, it is, so far it's quite easy. Then how can we come back to one of this list? So if J is true, then let's see, we can come back to one of the lists, and in this case, so equation AX equals 0 has only the trivial solution, which means there exists no free variable. So let's try to understand this. So we do not even think about the inverse yet, okay? Because we start from the very beginning with this item. So for some matrix A, which we don't know about their invariability or not, but that matrix A has this matrix C that satisfies C times A equals identity. So in that case, it is giving this this statement as true. So how can we prove that? So in short, if this is true, then this is also true. So again, C times A equals identity. So we do not know A is inverse or not, invariable or not, but someone said there exists some matrix C that satisfies this, and then it will lead to this homogeneous linear system will have only the trivial solution. Okay, how can we prove that? Okay, so the proof is as follows. So it's quite simple, but it requires a little bit of a tricky kind of technique. So you just multiply C on the left side of this homogeneous linear system. Okay, and so C exists, so that's our initial assumption. Then the resulting equation becomes this, because C times 0 will be just a zero vector, and then we know this guy will become identity matrix. So X is this. So for whatever X as your solution for this solution vector should always be this 0 vector. Okay, that means even if you started with some assumption that, okay, so what if our X is non-trivial vector, which is different or not equal to 0 vector, and then it always ends up with this thing, starting from this assumption, right? So that way, if this is true, and then this is also true. Okay, so here what we are discussing is, so we have one big list that are all logically equivalent. So A through what? A through I, and then L. And then we started from A, and then went to some outer item of this J, and then starting from J, we came back to one of the item D, which are also logically equivalent to A. Okay, so in this case, this J is also logically equivalent to this set. So this is not bigger or not smaller than this set. Or yeah, in terms of the true set, I mean, it's about the logics that we learned in high school, and also which is quite a big subject or topic that you might also study in some other class. But if this is true, and then let's suppose all the elements that satisfies this A. Okay, so for example, A is invariable, and then this guy is having like A, the reduced echelon form is an identity matrix. Okay, so consider these two statements, and then we can imagine the set of all the possible matrix A. Okay, so yeah, let's just simplify the situation where our matrix A is a 3 by 3. And then we collected, let's just imagine, we collected all the possible invariable matrix. Okay, so that invariable matrix and that set as, yeah, we call that set as maybe S and A, which means set of A. Okay, and then set of B, which is containing all the possible matrices, still in 3 by 3, but their reduced echelon form is identity matrix. Okay, we can imagine these two different sets of matrices. Okay, and then if logically, if A is true and then B is true, if someone says this relationship, then which set is bigger? I mean, which set is containing the other? Or which set is smaller? Okay, and then let's give a simpler example. So I am 40-year-old. So this is one statement. Okay, so I lived more than 40 years. And then I lived more than 30 years. Okay? Then let's think about these two logical statements. So if this first one is true, and then the second one is also true. But what about the other direction? If someone says, okay, I lived more than 30 years, and then it's not always true that I lived more than 40 years, right? So in this situation, if this guy was true and then the second guy is automatically true, then which one should be the bigger set? This guy is a bigger set. Okay, so A should be somewhere inside of the B. So in terms of the truth set, so it is called, yeah, we call that as a truth set. In that case, the second set should entirely contain the first set. So that is our proposition, or this. That is how this relationship becomes true. Okay, and then here the trick is if A is true and then B is true, and then also someone says B is true and then C is true. Okay, in that case, we can imagine the true set and their relationship as this: A and B and C. Okay, and then someone additionally says, okay, A and C are actually the same thing. So in that case, so B should include A, but that should be included in C. But someone says A and C is exactly the same thing, or exactly the same thing, and then our conclusion is A, B, and C. All the sets are just the same set of A, B, and C. Okay. So this is the main trick. that creates or that allows us this item J to be included in the our original set. Okay, so we started from A, and then we landed J, and then starting from J, we landed one of the other item in the same set. Okay, in that case, A and J and D, but actually D and A are the same thing. Okay, so that's how we can prove this logically equivalent things. Okay, so starting from A, and then we landed or we arrived at J, and then came back to our set. So we took care of the item J, and then let's think about the last item, this guy. Okay, so in this case, so we have still a freedom to choose any item in our set. So let's choose. Okay, so let me. AKG, AK. Okay, I didn't fully memorize the exact flow, but yeah, here we still start from this same item of A. A is invariable matrix. Then, how can we prove this guy is true? We can just simply plug in this A inverse into this place of D, and then that's when we can obtain or can prove that A times A inverse becomes identity. So starting from A, this item K is true. Okay, and then the last item or the third item that we want to come back is this guy, G. So here we want to prove this guy starting from K. If K is true, and then G is true. So that means AD is equal to identity. Then your equation AX equals B should have at least one solution for any vector B, which means AX equals B. So this guy should have at least one solution, should have always the solution for any vector B. So we want to prove this guy. How can we prove that?
X equal A minus 1B.
Yeah, right. Yeah, I was not clear. Yeah, so that is a good point. So here we do not think about, we do not assume A is invariable. So we only assume that this relationship. So again, although the definition of an invariable matrix is that CA and AC equals identity, if we can find such matrix C, and then that's the definition of the A matrix A being invariable, right? But let's just forget about that relationship. Okay, we just forget about it, but we only assume that there exists some matrix D that satisfies this, and then it will lead to the statement that your matrix, your linear system AX equals B should always have a solution, at least one solution for any vector B. What's that?
A times D times X equals BT.
Yeah, that is a good try. Yeah, A times D times X equals B. B times D, right? Yeah. So that is a good try. So let's try to use a similar trick that we used in the previous case. So we try to leverage or utilize this relationship. So D is multiplied on the right side of A, right? So we want to multiply D on the right of an A, and then we can think about this matrix D here, but this is not actually obtained by multiplying D on the right part. So in this case, if we try to multiply D on the right, then we cannot easily multiply D here because X is placed already on the right side of an A. So if you kind of multiply D, then it will be something like this, right? So we cannot easily obtain this, but yeah. So this is a little bit tricky, but yeah, it's almost close to the answer. So how can we do that? So let's imagine some vector, although we don't know what the vector y is, but let's imagine some vector y, and then AD times y becomes b. Okay, so for any given b, okay, and then so again, this equation is not related to this. We just created this equation, okay. So let's see if we can find the vector y in any cases, any vector b. So in this case, AD will become identity matrix based on the fact of this. And then if y becomes b, which means A times something becomes b, and then if that 네. Okay, give me a few minutes to just finish this, and then I'll distribute these answer sheets to you guys. So in this case, yeah, so it's time to just refresh our focus. Okay, so so in this situation where A is multiplied by some square, I mean not intending matrix or anything, it's just a kind of a question mark or some placeholder, and that is the same as B. Okay, and for whatever given B, if we plug this dy and then y becomes b, so if we plug d times b here in the place of this x, and then a times d will become just b. Okay, so this will be equal to the given b. So again, the main point here is that if we plug or if we replace this vector x as d times b, where b is given vector here on the right, in that case that will at least satisfy our linear system, which means d times b is one or at least one of your solution for this linear system. Okay, so again this assumption is true, and then if you set x as d times b, and then you can always find one solution at least. Okay, so that way, starting from k, we landed this guy g for any given b, any vector b. You can always find the solution for ax equals b. Okay, so we came back to our big list. So that way, we handled all the things. So they are all logically equivalent. And then it means, so one thing to note is, so from all these equations, or all the relationships where we integrated all the items into one logically equivalent set, and then so this is something like this. So A is B and C and A. In that case, A, B, C are the same thing, and then suppose A was logically equivalent to D, and then it is automatically saying that D is logically true with C and B, although we didn't directly prove it. But among the set, you can pick up any two items, and then they are logically equivalent. So that's what we just proved it. Okay, that's what we just proved here. So one thing that I wanted to emphasize here is this guy. So J and K. So J and K, those two items were part of the definition of an invariable matrix. Okay? And then we just proved that these two are logically equivalent, although we didn't prove directly, like the case of starting from K into J, and then starting from J, and then landing at K. We didn't directly prove it, but we actually integrated all of them into one set. So, as I mentioned, we can pick up any two, and then if that two item is these two, then they are logically equivalent. Which means if this guy, or one item, or one statement is true, then this guy is also true. So that actually answers some unanswered question when we studied the definition of an inverse matrix. So if you guys remember, when talking about when studying the definition of an inverse matrix, I just mentioned that if your matrix is invariable, then that inverse of matrix A will just satisfy automatically those two, right? But we didn't prove, or we didn't study why if one is true and then the other should also be true, right? And vice versa. But through this long list of the theorems or items, we now understand or prove that these two are logically equivalent. So if one is true and then the other should also be true, and then vice versa. Okay, and then let me ask some related question. Yeah, between these, in terms of the relationships between these two. So this question is the question that someone previously answered at the end of last class, but let's just think about some rectangular matrix, not the square matrix. So 3 by 4. So this is our matrix A. So again, from the definition of an inverse matrix, I kept emphasizing the following thing. So we only talk about the square matrix when discussing the inverse, right? But this is not clearly a square matrix, so this is a rectangular matrix. But so there should be no inverse here. But the question is there any matrix C that satisfies this guy? Or is there any matrix, for example, let's call that as D, that satisfies this? Or, so this was the first question, and then this was the second question, and then the third question is, can we find the matrix C that satisfies both of them? Okay, so this is a more strict condition, right? So let's try to answer those questions. So I didn't give you any details or any particular numbers that are filling your matrix in, but from looking at this matrix, you can at least answer some of the questions. So So this, in order to be able to answer these questions, we have to think about the size of a matrix. Okay. So C times A, then what should be the size of I? The matrix I mean the identity matrix, what should be the size of it? So A is 3 by 4, right? And so we can change this number 3 by changing the size of matrix C. But still, the number of columns should be 4, right? So that should remain as 4. So if this identity matrix should be at least a square matrix, right? So this is a square matrix still. So identity matrix is the 4 by 4 matrix. So A, which is 3 by 4, then we multiply some matrix on the left, and then we have to obtain this 4 by 4 matrix, right? I mean, in order to be able to call that as an identity matrix, 1, 2, and so on. Okay, so in this case, can we do or can we create or convert this matrix into this by multiplying some matrix here? Or you just use your matrix on the left and then multiply some matrix D and then create. So in this case it's a 3 by 4 and then D is a 4 by something. But in order to have identity matrix as a resulting matrix, this should be 3 by 3 matrix, right? So it's like this. So let's call that as I4 and I3. So is this possible, or in other cases, is the second case possible? So one of these two is definitely impossible. So I'm giving a hint for these questions. So one of them should be definitely impossible, and which one would be impossible? The first one or the second one? First one. Why do you think so? Why do you think the second one is possible?
It's more because you can
두 번째가 안 될 것 같아요. 왜요? 그거는 근데 얘가 모든 로우에 피벗을 가지면 어떻게 돼요? 그러면 이게 가능해지지 않아요? 그러니까 언제나 가능하다. 그러니까 언제나 불가능한 게 있어요, 이 둘 중에. 그러니까 가능한 거, 그러니까 언제나 가능한 건 없고 언제나 불가능한 건 하나 있어요. So among the two, one is always impossible. So that's my question. So which one is always impossible? So let's think about which case is sometimes possible. I mean, as a kind of opposite question. Which one is sometimes possible? So at least in the case of in the second case, which resembles some linear systems, right? So in that case, so for D, for example, D should have the size of 4 by 3, right? Then this first column can be represented as a linear combination of, I'm still talking about almost the same thing that I keep emphasizing. So the linear combination of those 4 green columns, that should provide 1, 0, 0. And then using another linear combination coefficient, we have to create 0, 1, 0, then another set will create 0, 0, 1. So in that case, it's yeah, it would be possible sometimes, right? It is sometimes possible, but in this case, it is not possible. I mean, yeah, I'm just giving you the answer. So, yeah, this is not possible, and so it is related to this. So in this case, so you are multiplying some matrix on the left, and so if you view this matrix as your ingredient, and then the ingredients should be rows, because it's on the it's the second matrix. So these three columns are rows, and then these three columns, linearly combining them, we have to create 1, 0, 0, and 0, 1, 0, 0, 0, 1, and 0, 0, 0, 1. Okay, for all the 4 different cases, by only using 3 vectors. So that way, this is not possible. So you have to create the 4 different vectors by using 3 different by using a linear combination of the 3 vectors. Okay. So it is something like this. So let's just reduce the dimension as 2, and then yeah. So instead of a 3 by 4, let's think about 2 by 3 matrix. Then you are given 3-dimensional vectors, right? And then you have to create 1, 0, 0, and 0, 1, 0, 1, 0, 0, 1, right? All the 3 directions that corresponds to our axis in this 3-dimensional vector. And then whatever 2 vectors that are given, you cannot linearly combine them to create all the 3 different directions. Okay, so that's the kind of intuition. Although I didn't give a kind of rigorous proof, but here you can think about this kind of something called a basis that we will learn probably in the next big chapter. But you only have like 2 ingredients, but you cannot create 3 different, or more formally, 3 linearly independent directions. Okay, and that is also related to the number of pivots. Although I'm not giving a full proof, but you can also think or intuitively understand this as follows. So in the matrix A, what is the number of maximum number of pivots? It's 3, right? And that 3 cannot. What about this guy? Although this guy is like a different shapes or different size of matrix, or 4 by 4, at least this matrix, or in 4-dimensional matrix, that will have 4 pivots, right? So by default, identity matrix is a simplistic form of a matrix that have the maximum number of pivots. So in this case, you have 4 pivots. Then you cannot create the matrix that have 4 pivots using the matrix having 3 pivots. So pivot is giving the so pivot is actually so pivot is the degree of freedom. So I keep introducing a new term that might confuse you more, but you guys kind of understand the idea. So you only so pivot is the number of actual ingredients that you have. Okay, and then the resulting number of pivots are the ones that you have to create or reconstruct them, and then you have more vectors that you have to create by using a smaller number of vectors, which is impossible. So this is not. Yeah, this is always impossible. Okay, so yeah, although I gave a little bit of a high-level explanations, but yeah, but the point is quite simple. So point is this theorem that we learned, which contains a lot of an item, but it's basically combining or integrating all the different pieces that we learned, okay, into a special form or special situation when your matrix is square. Okay, so if your matrix is square, if one of these items are true, and then it will make beautifully all the other items true as well. Okay, and then that is the meaning of this invertible matrix. Okay, so that's it for today. And then please pick up your exam answer sheet. So you didn't write your answer here? You didn't? Can you send me an email? I was taking a photo now. Different TAs did a grade on the different problems. Yeah, I connect you to TAs that distribute problems.
هل صح خطينا؟ عليك ها.
So take it. So the answer sheet or the question sheet?
네, 아니요. 우리가 있는 걸로 생각을 해야 될 것 같고.
네, 이거는 발이 깎인 거 아니에요.
5점에서
네.
2점? 그걸 미안하지만 다음 시간에 좀 알려줄게요.